Computer Science. This course is on operating systems. For the past few modules, we were looking at process synchronization, and today also we will continue to look at process synchronization with respect to a synchronization tool called semaphores. The learning objectives for this class is to understand what a semaphore is, to learn how semaphores can be used for synchronization, and to learn how a counting semaphore can be implemented using binary semaphores. So, cooperating processes are processes that share data. They will have some common data or common variable which they will be accessing, and when more than one process try and access common variables or common data structures, then there is a need for process synchronization. So, process synchronization can be achieved through many solutions, and there is a lot of solutions to the critical section problem. The critical section problem is nothing but each process has got a critical section of code which each process will be executing when they try to access the shared data. So, the portion of code within each process where they try to access shared data is called a critical region of code, and when a process executes the critical region of code or critical section of code, then there should be no interruption, it should be executed atomically, or you need to have some solution that is provided using synchronization tools to solve this critical section problem. And many solutions are there for two processes, for multiple processes. We saw a number of solutions for two processes as well as multiple processes. So, today in this class we learned about a synchronization tool called semaphores, which is used to provide a solution to the critical section problem. So, the semaphore is a tool does not require busy waiting, and the semaphore, what is a semaphore? It is nothing but an integer variable, and that integer variable will have some initial value that is being set. Based on the initial value, so many number of people can access the shared resource. So, if you have a shared resource, you can have a semaphore that will guard over that shared resource, and that initial value of that semaphore will be nothing but the number of processes who can access this shared resource at a particular time. So, if it is a shared resource which can be accessed by only one process, then the initial value of the semaphore is set as 1. Else the initial value will be set to accordingly to how many number of processes will have to access that common semaphore, and this can access that common shared variable. So, this semaphore can be accessed only using two atomic operations. So, these atomic operations or the indivisible operations that can be performed on a semaphore are called the wait operation and the signal operation. The wait operation is also called the P operation, and the signal operation is called the V operation. And if you look at this wait operation, the implementation of the wait operation on the semaphore will look something like this. You have the semaphore S, and you will have some initial value of the semaphore. So, any process which wants to enter critical section will first perform this wait of the semaphore. It will check if the value of S is less than or equal to 0. If the value is less than or equal to 0, it will do no operations and keep on waiting. Only if the value of the semaphore is a positive value, it can continue. So, if the value of the semaphore is a positive value, if it is 1 or above 1, then it will decrement the value of the semaphore. So, if you can see that the wait operation is nothing but basically decrementing the value of the semaphore, provided the value of the semaphore is some particular value based on which the process can proceed. And then the next operation that you can do on the semaphore is the signal operation. In the signal operation, the value of this semaphore, it is actually an integer value, is incremented. So, you do an S plus plus for signal operation. So, this wait and signal operations are the only two operations that you can perform on a semaphore. So, the semaphore cannot be accessed or manipulated with any other operation. only it can be manipulated, or you can be access the semaphore only using this wait and signal operation. Now look at this critical section of n processes. We will see that how when there are n processes, the semaphore can be provided to provide mutual exclusion. So there is a semaphore called mutex. So this mutex is a semaphore, is the name of the semaphore. Mutex is the name of the semaphore, and it is given an initial value. The initial value is set to 1, and this mutex semaphore is used to safeguard some shared resource. So any process before entering the critical section, it will have to wait on this mutex semaphore, and then it will enter critical section, and then it will signal mutex and go to the remainder section. So here you can see that this will proceed in this manner. You got processes P0 and P1, and mutex is the semaphore. So the initial value of the semaphore is 1, because the only one process can access the shared resource at a particular time. That is why the initial value is 1. So first process P0 wants to enter critical section, it executes the wait operation, and it will check if the value of the semaphore mutex is less than or equal to 0. The value of this mutex is not less than or equal to 0, it is 1. So it can decrement the value of mutex, and process P0 can enter critical section. And when P0 is present in the critical section, say if P1 wants to enter critical section, P1 will have to execute this wait operation on the semaphore mutex before it can enter critical section. But while executing this wait operation on this mutex semaphore, P1 will try to check if the value of this mutex is less than or equal to 0. It finds that the value of mutex is equal to 0. Since the value of mutex is equal to 0, P1 cannot enter critical section. It keeps on waiting in the while loop. So in the while loop, it keeps on checking while mutex is less than or equal to 0. It keeps on checking. Whenever it gets a CPU, it will try and check if the value of mutex is less than or equal to 0. It will not be, it will be equal to 0, and then it will keep on waiting. And when process P0 comes out of critical section, say, when process P0 comes out of critical section, it will execute the signal operation. It will execute signal of mutex. So signal of mutex is actually incrementing the value of mutex. So mutex value becomes 1 now. And now when process P1 tries to execute wait on mutex, it checks the value of mutex. It finds that the value of mutex is 1. It is not less than or equal to 0. So process P1 can continue to enter critical section. It will decrement the value of mutex and makes it 0 and enters critical section. So this process P1 is allowed to enter critical section only after P0 comes out of the critical section. And when P0 is present in the critical section, P1 is not allowed to enter critical section because the value of mutex will be 0, and this process cannot enter critical section. And after coming out of a critical section, process P1 can change the value of mutex to 1, and it will do a signal operation to change the value of mutex to 1. So here, using semaphores, we see that the critical section problem is solved, and it provides mutual exclusion. And we look at the implementation of the semaphore that we had seen now. We see that the disadvantage is busy waiting. That is, there is a while loop while less than or equal to 0 semicolon. That is, the process keeps on checking whether the value of s is less than or equal to 0. And this process will loop continuously in the entry section. But the process is not in critical section, it is waiting to use a CPU, and there is only one single CPU. Unnecessarily, one process which is waiting, keeping on checking the value of the semaphore, will waste CPU cycles. But in the case of multiprocess systems, this is not a problem. So such a kind of a semaphore where it continuously checks the values is called a spin lock. But spin lock is useful in multiprocess systems because you have multiple processors, so there is no scarcity of processors. You have many processors, and unnecessarily if this process is not checking and is waiting, it may waste some time. So even if it is getting the CPU, and if it keeps on checking this value of semaphore, no context switch will be needed. Okay. So, it can keep on checking, if it becomes available immediately it can enter critical section. So, no context switch is required when a process is waiting on a lock, and this is very useful when the locks offer a short duration of time. So, to avoid this, they tried to give a different kind of implementation for semaphores. So, how is this implementation done? The semaphore, rather than looking at as a single variable, it is looked at or it is implemented as a structure or a record. So, this structure has got two members. One is the actual value of the semaphore, as how we had given the value for the variable, and then you have an array of processes also associated with it. So, the semaphore is a value and a list of processes associated with the semaphore. And here we define two operations, that is block is an operation that suspends a process, that is invoking that operation, and then you have wake up of P, which helps to resume the execution of an already blocked process. So, how will these semaphore operations be defined now? You have wait of S defined in this manner. So, S is a semaphore which is a structure which has got a value and a list associated with it. So, first during wait operation, the value of the semaphore is decremented, and if the value of the semaphore goes less than 0, then it means that the process should not be allowed to access critical section. So, what is done? This process is added to this S dot L, that is the list associated with the semaphore. This list can even be something like maintaining a list of process control blocks corresponding to each of the process. So, this list, you are adding this process to the list, maybe you can add it to the end of the list, and that process is put to the block state or it is moved to the waiting state, and this process will be woken up only when this semaphore becomes available. Till then it is put to the sleeping state. So, what is done in wait? You decrement the value of the semaphore and you check if the value of the semaphore becomes less than 0. If it is less than 0, this cannot access the resource, and hence the process is added to the list associated with the semaphore and it is blocked or put to the waiting state. And now what happens with the signal operation? In the signal operation, you increment the value of the semaphore, and then you see if the value of the semaphore is still less than or equal to 0. Then what does it mean? If it is still less than or equal to 0, we have already actually increased the value of the semaphore, which means that one process can use the resource now. So, you try to now check if there is any process which is waiting in that queue associated with the semaphore. So, when will a process be waiting when a queue associated with the semaphore? Even after incrementing, if the value still remains less than 0, or if it comes to 0, then it means that there is already a process waiting in the list. So, if there is a process waiting in the list, you remove a process from the list and then you call wake up of P. That process which was sleeping or which was in the block state is now woken up and it is brought to the ready state, and that process can be given the CPU next. So, this is what happens during a signal operation. So, here we are seeing that the wait and the signal operations that we saw first have been modified slightly to avoid spin locks or busy waiting, and we have tried to put the process to a sleeping state rather than making it keeping on checking the value of the semaphore repeatedly. So, here we will see how a semaphore can be used as a synchronization tool when it is synchronization tool when a common resource is being accessed. So, here just an example where flag is a semaphore which is initialized to 1, and you have two processes PI and PJ, and there is a common resource. This resource is safeguarded by the semaphore flag, and the initial value of the flag is set to 1 because only one process can access this resource at a particular time. So, PI process waits on this flag before it wants to enter critical section, it will make the value of flag equal to 0 and access the resource. That is, it is decrementing the value of the semaphore and accessing the resource. And then Pj wants to enter critical section, so it also waits on flag, but finds that the value of flag is equal to 0 and it is put to the waiting state. And when Pi signals after coming out of the critical section or after accessing the resource, after finishing to access the resource, process Pi signals flag, it increments the value of flag to 1 and it comes out of the critical section. And now process Pj finds that the value of flag is equal to 1 and hence based on that it accesses the resource. It will change the value of flag to 0 and access the resource. After finishing to access the resource, it will signal the flag value. So thus, like this, you can use the semaphore for safeguarding a resource, and when you are using the semaphores, it is possible to have a deadlocked and starvation kind of situation. So what is deadlock? When two or more processes are waiting indefinitely for an event to happen, and that event can be caused only by one of the waiting processes. So you have a set of processes and every process in that set is waiting for some event, and that event can be caused by only one of the other processes that is present in the set. So that process which needs to cause this event is also waiting. Okay. So that process will not make this event to cause. So every process is waiting. They also may have to cause some event to happen, but that will not happen because each of the process is waiting. So this will lead to a deadlock situation, in the sense no process will be able to proceed further. And now we will see how this deadlock and starvation can happen with semaphores. So assume you have got two semaphores S and Q, and each of the semaphores is initialized to a value of 1. That is, each of them is safeguarding a resource which can be accessed by only one process. So now P0 and P1 are there. P0 first executes wait of S. So P0 will execute wait of S and it will make the value of S to be equal to 0. And P1 will execute a wait of Q, executes wait of Q, and that will make the value of semaphore Q equal to 0. Now P0 executes wait of Q, but P0 finds that Q semaphore is already been held by some other process. So that is been held by process P1, and P1 executes wait of S. So value of S is now 0. So this P1 also finds that S is currently being held by some other process. So process P1 is also waiting. So here we find that both of the processes are supposed to access some resource, but each of them is waiting for the other process to release the semaphore. So both are holding some resource and they are trying to get the resource which is held by the other process. So each one is waiting on the other one. So P0 is waiting on P1 and P1 is waiting on P2. So this continues forever. So this leads to a deadlock kind of situation. So when we are using semaphores for a solution to this critical section problem, we need to ensure that the semaphores are used in a proper sequence such that they do not result in a deadlock and a starvation kind of a situation. So starvation, how can starvation happen? This is indefinite blocking. That is, a process may never be moved from the semaphore Q in which it is suspended. So we saw that when you put a process to the waiting state, you add it to the semaphore's queue and is kept waiting. And suppose if you are adding process again and again to the end of the queue, but when you are releasing, if you are releasing the process only from the end of the queue, then in the LIFO manner, last in first out manner, then in that case the process that was earlier added to the queue may not be able to finish at all, may not come out of the waiting state at all. So you need to ensure that the starvation is also not happens in this kind of an situation. Now, having seen the operations that can be performed on semaphores, we will now look at two different kinds of semaphores that are possible. There are two types of semaphores that are possible. One is a counting semaphore and the other is a binary semaphore. So what do you mean by a counting semaphore? the counting semaphore can take values, any integer value from 1, 2, 3 etc. and so on. And the binary semaphore can take only 2 integer values. It can only take a value between 0 and 1, that is, it can either be 0 or it can be 1. But and it can be simpler to implement binary semaphore than the counting semaphore. But now we can implement a counting semaphore using binary semaphores. So we will see how you do that, and the data structures that we use for implementing a counting semaphore using binary semaphores are these. You have 2 binary semaphores, S1 and S2, and there is an integer variable C, and initially the binary semaphores S1 and S2 are initialized to 1 and 0 respectively. The initial value of the semaphore is copied onto C, or C has the initial value of the counting semaphore S. What is S? S is the counting semaphore, and counting semaphore can take any initial value, say it can be 4 or 5 or any number, and the binary semaphore can take values only between 0, 1 and 0, can be either 1 or 0, and the initial value of semaphore S is set to C. And now we will see how the implementation of the binary semaphore will be. The binary semaphore implementation will look very simple. For the wait operation on a binary semaphore, it will just check if the value of the semaphore is equal to 0 or not, because the binary semaphore can take only values 0 and 1. So if the binary semaphore's value is 0, then it means that the resource cannot be accessed. And if the binary semaphore's value is not equal to 0, then you decrement the value of the semaphore. The value will be 1 and just decrement the value of the semaphore. And for signaling, just increment the value of the semaphore. Now we will see how to implement a counting semaphore. So here the wait operation on the counting semaphore can be implemented using wait and signal operations on binary semaphores like this. So first the process will wait on S1. So S1 is a binary semaphore, that is, it will check if the value of this binary semaphore is 1. If it is 1, then it will decrement and then carry on to decrement the value of C. C is actually the counting semaphore's value, the total number of processes who can access the shared resource. So C is decremented by 1, and if the value of C becomes less than 0, then it will just wait on another semaphore called S2. And then only when a signal is being done, signal operation is being done, this process can be moved from the waiting state. And then you do a signal of S1. And if you look at the signal operation again, it will wait on this binary semaphore S1, it will increment the value of C and check if the value of C is still less than or equal to 0. If it is less than or equal to 0, it will signal the S2 semaphore on which other processes are waiting, else it will signal the S1 semaphore. So we will see how this counting semaphore is implemented. We will see an example. So let C equal to 2 be the initial value of the semaphore, which means that there is a resource which can be accessed by only 2 processes at a particular time, at the same time. Now how will wait of S be implemented? If you look at the algorithm, here you can see that there is S1, S2 value of C which have been manipulated. So how will first wait of S1 is executed? So you have S1, initial value of S1 is 1 and S2 is 0, initial value of C is 2. When wait of S1 is executed, the value of S1 becomes 0, and then you try and decrement the value of C. C becomes 1, and then look at the algo, you check if the value of C is less than 0. Here the value of C is not less than 0. So what you can do is just signal S1 and come out. So signal S1 and come out. Now if another process again executes wait of S. So what does it do? The value of S1 is now 1, the value of C is 1, value of S2 is 0. So it will decrement the value of S1, wait on S1 will decrement the value of S1, it will become 0. It will decrement the value of C, C becomes 0, and the algorithm check if the value of C is less than 0. the value of C is not less than 0. So, it just signals S1 and comes out. And now this process is the first process which executes this wait can enter critical section or can access the resource. The second process who executed this wait can also access the resource. Now, if a third process comes into picture, it will also execute wait of S. So, that will make the value of S1 to 0 and then it will try to decrement the value of C, it will become minus 1. Now, the value of C becomes minus 1. So, if you look at the algorithm, you see that you have C less than 0 and you execute signal of S1. So, signal of S1 is done which means that you make this value S1, but the process is made to wait on S2. So, the process waits on S2. So, here the process is made to wait on S2. So, here you find that when the number of processes becomes more than the initial value of C or becomes more than how many can actually access the resource, the third process is now put on to the waiting state. It waits on semaphore S2. Now, what happens when a signal is being done? We will see. We continue with the state where we had left during the wait operation. The value of semaphore was S1, the value of C was minus 1, the value of S2 was 0 and a process is waiting on this semaphore S2. And now look at the code for signal, you have wait on S1, increment C and then continue. So, wait on S1 will decrement the value of S1 to 0, you increment C, C becomes 0 and now you check if the value of C is less than or equal to 0. So, when the value of C is less than or equal to 0, it means that there is another process which is waiting on that semaphore S2. So, since the value of C is equal to 0, it will do a signal of S2. So, S2 now becomes 1. When S2 becomes 1, the other process that we saw now, the third process which executed wait, which was waiting on S2 semaphore, that can now come out of that waiting state and it can try and access the semaphore. So, because there was one process which is waiting, which is now signaling, so that process can come out of the waiting state. So, process that was waiting on S2 is now released. So, the release process, what does it do? It will signal S1, okay, and hence S1 becomes 1. And suppose if there is another signal, the second process also which was using the resource is now signaling, it will again wait on S1 and it will increment C, C becomes 1, but now the value of C is not less than or equal to 0, it will just signal S1 and it will come out of the critical section and will signal 1. So, now S1 is also released. So, here you find that the counting semaphore can be implemented using binary semaphores. So, in today's class we learnt about semaphores. We saw how semaphore can be used as a synchronization tool, and then we learnt about counting and binary semaphores. We saw what counting semaphore is, what binary semaphore is, and then we saw how you can implement a counting semaphore using binary semaphores. So, the references, thank you.